Welcome to this presentation of the IEEE Globecom 2018 paper, 5G mmWave Downlink Vehicular Positioning. This is a collaboration between Chalmers University of Technology, Hanyang University, and the Universitat Autónoma de Barcelona. The list of co-authors is shown here. My name is Henk Wijmers. The 5G positioning challenge is as follows. We consider a base station with an antenna array, a user equipment with an antenna array, and a signal going over a complex propagation environment. We would like to answer the following questions. From the signal received from a single base station in this unknown propagation environment, is it possible to determine the user's position, the user's heading, and also the user's clock bias, since generally the user and the base station are not synchronized? Moreover, is it possible to build up a map of the propagation environment? And finally, can we do this even when the line of sight path is blocked? The answer will turn out to be positive to all of these questions, as we hope to show in this presentation. Radio signals have always been used for positioning. This is because radio waveforms convey information about the propagation environment. Consider this scenario where there is a transmitter sending a signal to a receiver, which is able to sample the received signal at a very high resolution. Then what the receiver would see is shown, for instance, on the right. The first arrival path could be the line of sight path, which tells us something about the distance between transmitter and receiver. The non-line of sight paths would tell us something about the propagation environment. In practice, we will not have such high resolution information available, but other kind of measurements can be taken, such as signal strength, time-based measurements, or angle-based measurements. These measurements are then converted to distances or angles and then to positions. For instance, if we can take distance measurements with respect to 3 base stations, we can determine the position of a user. Similarly, if we have angle measurements with respect to multiple base stations, we can also determine our position. So here, this presentation will consider a mix of distance and angle information. With the introduction of 5G new radio, new positioning opportunities open up. This is because 5G has several properties that are very useful for positioning. First of all, 5G will work in high carrier frequencies, which lead to a relatively sparse geometric channel. This means that there are few propagation paths, and these paths can be related to the propagation environment. Secondly, we will have large bandwidths, which will provide us high delay resolution. So we can distinguish paths with a small difference in delay. Since we have large number of antennas that transmit and receiver in millimeter wave frequencies, we will also get high angle resolution. So multiple antennas at the receiver provides high angle of arrival resolution, while multiple antennas at the transmitter can provide high angle of departure resolution. We will also have device-to-device communication, which allows cooperation between devices. So devices will exchange signals from which they can estimate relative distances and angles, which will boost up positioning performance. Finally, because of network densification, there will be many base stations, so the probability of a line of sight path will be relatively high in 5G new radio. And of course, the line of sight path is the one that is most useful for positioning. In order to better grasp the 5G millimeter wave positioning problem, we decompose it into the following parts. We have the standard data communication, which is interrupted periodically, let's say every 100 milliseconds, for the transmission of downlink reference signals, for instance a pilot reference signal. Such a signal is sent to the user, which then receives an observation as shown in the equation on the bottom. Here y of t is the observed waveform across the antennas, w is a combiner, l is the number of paths, hl is the channel matrix corresponding to one of the paths, which contains complex channel gain, angle of arrival, angle of departure. F is a precoding matrix, X is a training signal, and tau L is the delay associated with the alt path. Finally, there is noise. The receiver estimates the parameters of this channel, so the delays and the angles, after which we move on to a data association step. In the data association, the estimated angles and delays are associated with prior map information, so that we can exploit such map information. Then we go on to positioning and mapping, in which we refine the estimate of the user's position and also improve the map. After that, the user moves according to some mobility model, and we wait until the next request for a position information. Position information can be used at various stages here in this flowchart, but is not discussed here in detail. For those of you who are interested, we have provided a small MATLAB implementation of the channel estimation routine as well as the positioning routine on GitHub in the link below. We now formulate our problem more mathematically. We have a user with an unknown position XUE, with an unknown heading alpha, and a base station located here. There is a signal from the base station to the user. There's a line of sight path shown in green, and then there are multiple non-line of sight paths shown in red. There are different types of non-line of sight paths. There are non-line of sight paths that go over via a scatter, for instance here S1, to the receiver. And there are non-line of sight paths that go via a reflecting surface, for instance with an incidence point here, XS3. A reflecting surface can be described in different ways. For our purposes, it is useful to describe it through a virtual anchor, which is the reflection of the base station with respect to that surface. As the user moves along its path, the incidence points XS will move, but the virtual anchor location will stay the same. Also, as the user moves, the scattering point will remain unchanged. Possibly prior map information is available. This means that for some of the virtual anchor, maybe we have some statistical information. The user does channel estimation and provides its following observations. Estimates for each of the observed paths in terms of delay, angle of arrival, and angle of departure, with some measurement noise. It is clear that the angles and delays are a function of the user's state. Here the state includes the position, orientation, and also possibly the clock bias, as well as the map. However, the inverse relationship is not trivial. Let us now look at the data association. So in the data association, the question is the following. How can the channel estimates, so the path parameters, delay, and angles, be associated with prior map information? The way we proceed is as follows. For each path L and each map entry M, we compute a likelihood function SLM. So this is the likelihood that map entry M was generating path L. We also have one new map entry per path, because a path could have come from a new source which was not previously seen. We then find the best global association between the map entries and the paths in order to assign each path to an entry in the map, either an existing entry or a new entry. Thus, we make hard decisions, which tends to work well when the sources are well separated and there is no clutter. The best global association is found by solving the following optimization problem. We take the log likelihood function, and then we have association variables XLM that are binary, which tells us whether or not path L is associated with map entry M. We make sure that each of the paths is associated to at least one map entry, and that each map entry is associated to at most one path. The following animation shows the data association in action. We have a user, let me rewind, located at the blue cross. In this environment, there is also a base station, and there are 4 virtual anchors, one here, one here, one here, and one here, corresponding to reflecting surfaces. There are also a number of scattering points in the environment marked with the blue triangles. The dome around the user is a visibility in terms of the scattering points. So only scattering points within this visibility region are seen by the user. However, at any time, all of the reflecting surfaces are seen. At each time, the user sees a number of paths, a line of sight path possibly, and also a number of reflected paths. For each path, it needs to then decide whether it was line of sight or something new. In this case, we see that the user has seen a non-line of sight path that it doesn't know what the source is. So it could be a virtual anchor, but it could also be a scattering point. It has seen here another path, which it could be a scattering point or a virtual anchor. Only by moving will the user be able to resolve this ambiguity. As the user moves, after some time, it has decided that here is a virtual anchor and it can remove the assumption of the scattering point. From then onward, this virtual anchor can be used to improve the positioning quality. As the user goes around in the environment, more scattering points become visible. By now, all the virtual anchors have been found and are part of the map. The user continues forward. There was one scattering point at the beginning that it was not able to resolve, but by revisiting later, it sees, there was a scattering point. And then he goes again. Now we move on to positioning and mapping. The way that we proceed is we look at the joint distribution of all the unknowns. The user location, the user orientation, the clock bias, virtual anchor locations given the measurement, and also given the association. So we assume here that the association has been performed. We factorize this distribution due to independence among the priors and also independence of the measurements. Given this factorization, we can then create a Bayesian graphical model or a factor graph. This is simply a graphical representation of the factorization seen in the previous slide. The factor graph involves variable nodes, such as this one, XUE, and factor nodes, for instance this one. Factor nodes can correspond to prior information or to likelihoods. We can then run belief propagation over this factor graph to compute approximate posteriors of the variables. The colors and the numbers show the schedule of the belief propagation. Essentially, at the first time step, marked 0, we send information from the priors and information from the angle of departure of the line of sight path, because all of these can be informative. In the second stage, we send information over the edges marked in yellow and then over the edges marked in blue. At that point, we can start iterating between different stages. Messages can be represented in a variety of formats. Here we have chosen a particle format. After a sufficient number of iterations, we stop the iterative processing and we compute beliefs, which are marginal posteriors for each of the variables. We now apply these ideas to a specific simulation environment. We consider a scenario as shown in the figure with 4 vertical walls, a fixed base station, and a user location also fixed. For each wall, there is a virtual anchor location shown here. We fix the measurement standard deviation to relatively low values. We assume that the user has a relatively uninformative prior information with standard deviation in the horizontal plane of 3.2 meters. Among the virtual anchors, we say that for 3 of them we have some prior information with 10 meter standard deviation, while for the last virtual anchor we don't even know that it exists, so we have uniform prior information. We set parameters for false alarm, detection probability, and new target rate, and we use 2000 particles to represent the messages. We consider 4 different cases. We consider the case where the bias, the clock bias between the user and the base station is known or unknown, and when the orientation of the user is known and unknown. This gives in combination 4 cases. We commence with a Fisher information analysis. The x-axis shows the number of non-line of sight paths, so these are paths in addition to a possible line of sight path. The y-axis shows the position error bound. This is a fundamental lower bound on the achievable positioning accuracy expressed in meters. The figure shows a number of different curves for different situations, whether or not the line of sight path is available, whether or not the clock bias is known, and whether or not a map is available. Let's look at a number of these curves. First, this case, which corresponds to non-line of sight only and an unknown clock bias. This is the hardest case and leads to the highest PEB. We see that for this case, when more non-line of sight paths are available, performance improves. This is actually true for all of the cases. More interesting is that when we have 3 non-line of sight paths, but not a line of sight path, the system is identifiable. This means we can estimate all of the parameters. When we have less than 3 non-line of sight paths, the system is no longer identifiable, and we cannot estimate the parameters. When in addition to the non-line of sight paths, we also have a line of sight path, we move on to this curve. This curve corresponds to the case where there's line of sight plus non-line of sight, but with an unknown clock bias. We see that we have a huge drop in the PEB, and also the system becomes identifiable after one non-line of sight path. When we further add map information, we see that around the point of identifiability there's no real improvement, but later on we see a vast improvement due to the map information that we can exploit. We can draw similar conclusions regarding the other curves. It is interesting to note the following intermediate conclusions. We have sufficient conditions for localization and synchronization in terms of identifiability. We need either line of sight with one non-line of sight path in order for the system to be identifiable. It does not matter whether map information is available or not. Alternatively, we need 3 non-line of sight paths, or finally, we can also do with 2 non-line of sight paths, but with the prior map information. So these are interesting conclusions regarding the identifiability and when we can actually perform the localization and synchronization. This slide shows the data association performance. On the x-axis, we have the user clock bias uncertainty expressed in meters. On the y-axis, the data association error probability. So the probability that there's a mistake in the data association. We have a number of different curves again, based on which measurements are used to perform the data association. Let's focus on the case where we have high clock bias uncertainty. We see that there are 2 curves with very poor performance. This is the red and the green curve. The red and the green curve correspond to when we use the time of arrival estimate in the data association. So this means that when the clock bias is very unsure, it does not make sense to use time of arrival estimation in the data association. It will actually negatively affect the performance. The curves on the bottom here correspond to the case when we do not use the time information, at least the time of arrival estimate for doing the data association. We also have different curves for known and unknown user orientation. So for instance, we see here the dark blue curve. When the user orientation is unknown, corresponds to the case where we use the azimuth information. So when we use the azimuth angle of arrival information, the performance is degraded. This is because azimuth angle of arrival information is related to the user orientation. In case we don't use the azimuth angle of arrival or the time of arrival, which is this pink curve, we actually have really good performance. And it doesn't matter whether or not the user orientation is known or whether the user's clock bias is known. So the conclusion here is that measurements related to unknown parameters, for instance time of arrival with an unknown clock bias, should be ignored in the data association. Once the data association is completed, we can go on to the belief propagation for localization. This figure shows, as a function of the iteration index in the belief propagation, the root mean square error of the user's location. The horizontal lines correspond to Kramer-Rao bounds. The full lines correspond to the results of our algorithm. We see basically 2 groups of curves, the group on top and the group below. The group on top corresponds to the case when the clock bias was a priori unknown, while the group below corresponds to the case when the clock bias was known. The different curves within each group correspond to the case whether or not the user orientation was known. We see that when the clock bias was unknown, this incurs a huge penalty compared to the case when the clock bias was known. We also see a large gap with respect to the corresponding Kramer-Rao bound. This means that lack of synchronization incurs a severe penalty in the positioning. However, lack of knowledge of the user's orientation has only very limited performance penalty. This here shows similarly the synchronization performance. X-axis is iteration, the belief propagation, the y-axis is the root mean square error of the bias. Again, 2 groups of curves, the one on the top and the one on the bottom. The one on the top corresponds to a priori unknown clock bias, while the 2 on the bottom corresponds to a tight prior on the clock bias. Again, we have a large performance penalty due to lack of synchronization and a large gap with respect to the Kramer-Rao bound when the clock bias was a priori unknown. For orientation performance, we see that for all cases, we actually have relatively good performance. So the orientation estimation quality does not depend significantly on prior information regarding the bias or the orientation. Finally, we show the mapping performance. On the x-axis, again, iteration index. On the y-axis, the root mean square error of the virtual anchors. Again, different groups of curves, whether or not the clock bias was known or unknown. And also within each group, we see different performance for virtual anchors for which we had some prior information and for which we had not. So what we can conclude is that there's only a small difference for virtual anchors with a concentrated versus a vague prior. On the other hand, a priori synchronization is very useful for improving the map. We now go to our conclusions. Radio signals have always provided location information across all generations of cellular communication, as well as through GPS and other systems. The regime of having very high carrier frequencies with large bandwidth and many antennas is an interesting one for positioning. In particular, with 5G New Radio, we see new opportunities. For instance, for single anchor positioning, for heading estimation, for synchronization, and for environment mapping. Essentially, 5G mmWave can serve as a new kind of radar. Our contributions in this paper were a Fisher information analysis that can provide insight into identifiability, and a method for 5G localization in the presence of unknown reflecting surfaces, and in the presence of an unknown user clock bias. We have a follow-up paper at the 2018 Asilomar conference. This work was supported in part by the European Commission under the 5G car project, as well as the Marie Curie actions, and Vinova. Thank you.